Hello and welcome. In this video, we are going to talk about the birthday paradox. Suppose I asked you how many people need to be in a room for two people to have the same birthday with 50% probability. What would your answer be? To most people's surprise, the answer is 23. If there are 23 people in the room, then with more than 50% probability, there will be two people sharing the same birthday. In fact, there's a stronger version of this paradox, which says the following. If there's 70 people in the room with 99.9% probability, or with almost certainty, there will be two people sharing the same birthday. Do you find this surprising? The first time I came across this paradox, I did not believe it. I had no intuition for why it was true. That's why I decided to make this video, hoping I can help you make sense of this paradox. First, we're going to make some assumptions. The first assumption is we will only consider years with 365 days. We're doing this to keep things simple and not having to analyze two different cases. Second, there are no twins in the room. If there are twins in the room, then with absolute certainty, there are two people who share the same birthday, and that's not an interesting case. And the third assumption, people are born uniformly at random. This means people are likely to be born with the same probability on any given day, which in this case will be 1 divided by 365. And the fourth assumption, this is a very important one, people are born independent of each other. Suppose there are two people in the room. Let's call them person A and person B. The day that person A was born has absolutely no effect on the day that person B was born. And likewise, if there are two groups of people, group C and group D, the days that people from group C were born has absolutely no effect on the days that people of group D were born. Do these assumptions model the real world? Not really, but it makes it so much easier to analyze the problem. For instance, people are not born uniformly at random. On my blog, I've linked to a webpage that has statistics about days people are born on. I'm using a heat map from that website here. As you can see, people are not born uniformly at random. There are more people born in September than any other month, and that makes sense since they were probably conceived in December, during the holidays. Now let's talk about notation. Since this problem deals with a lot of probabilities, it might be a good idea to start defining an event. Suppose there are k people in the room, and let A subscript k, or what I'll call it, AK, be the event where all k people in the room have a different birthday. And this is the notation for the probability associated with that event. Or it's the probability that all k people in the room have a different birthday. Next, we're going to talk about our plan of attack. How do we prove this paradox? Now, since we defined the event, we're also going to define the complement of the event, which is the opposite of the event. Or, in this case, that would be since AK was the event where all k people in the room have a different birthday, the complement of AK is the probability that, or is the event that at least two people in the room have the same birthday. Now, from the law of total probability, we know that the probability of an event, plus the probability of its complement sums up to 1. We're going to use this fact a lot. Our goal is to first show that when there are 23 people in the room, all of them have a different birthday with probability less than 0.5, and then we're using the law of total probability. This would imply that the probability of at least two people sharing the same birthday is more than 0.5, proving the birthday paradox. Now let's talk about an idea which we will use over and over again. Suppose there are k-1 people already in the room, and a new person arrives. Let's call them person k. In order for all k people in the room to have a different birthday, the following statements need to be true. First, all the k-1 people who entered the room before the kth person needs to have a different birthday, and the kth person needs to have a different birthday from all the k-1 people already in the room. The idea that we presented here is crucial, and we're going to use it when we attack this problem. I highly recommend pausing this video and thinking about this for a bit. I'm going to represent this problem as a graph. On one side we have people, and on the other side we have days. We have 365 days here. Now, suppose a person walks into the room. We want to know, what is the probability everyone in the room has a different birthday? We are going to color the days. A blue day represents a day that is available, or a day that nobody has a birthday on yet. When person 1 enters, there are 365 blue days. The probability that person 1 has a different birthday is the number of blue days divided by 365, which is 1. A much simpler way of thinking about this is, if there's a single person in the room, then everyone in the room has a different birthday. Suppose person 1 was born on day 1. We are going to represent an edge between a person and a day to signify that a person was born on some day. In this case, we're going to have an edge between person 1 and day 1. I also want to mention that day 1 does not necessarily mean January 1st. It's just a placeholder. In this case, for person 1's birthday. Now, a day turns red when someone, in this case person 1, has a birthday falling on that day. Blue means available and red means taken. Now, let's analyze a more interesting case when there are 2 people in the room. Now, there's one person, and let's say another person walks in. We're going to make use of the idea we presented in the previous slide. In order for everyone in the room to have a different birthday, all the people who entered the room before the last person needs to have different birthdays, and the person entering needs to have a different birthday from everyone else already in the room. When person 2 enters the room, there's 1 day taken, so there's 1 red day, and there are 364 blue days, or days that no one in the room has birthdays on. Now, the probability that everyone has a different birthday, using the principle presented here, is the probability that person 1 has a different birthday times the probability that person 2 was born on a blue day. All we're doing is we're taking these principles presented here and we're translating them into equations. All the people who entered the room before the last person needs to have different birthdays. In this case, person 1 entered the room before person 2. So person 1 needs to have a different birthday times the probability that person 2 was born on a blue day, or the probability that the person entering the room needs to have a different birthday from everyone else. We know the probability that of person 1 having a different birthday is 1 from a previous slide. We also know the probability of person 2 being born on a blue day is 364 divided by 365, using our assumption that people are born uniformly at random. And when we multiply both of them, it turns out to be 0.997. Now let's assume person 2 was born on day 2. So now we have an edge between day 2 and person 2, and day 2 turns red. Now suppose a third person walks into the room. We will call them person 3. We will use the same principle we used before. We must know that the 2 days are taken, or are red, and 363 days are available or are blue. Now the probability that everyone in the room has a different birthday, using the principles above, is the probability that person 1 and person 2 have a different birthday, times the probability that person 3 was born on a blue day. We get this quantity here from this statement. All people who entered the room before the last person needs to have different birthdays. So person 1 and 2 entered the room before person 3. So they need to have different birthdays, times the probability that person 3 was born on a blue day, or on a day that neither person 1 nor person 2 are born on. We computed in the previous slide that the probability of 2 people having different birthdays is 364 divided by 365, and the probability that person 3 is born on a blue day is 363 divided by 365, if we assume people are born uniformly at random. And when we multiply this becomes 0.994. Now let's also assume person 3 was born on day 3, so now we have an edge between this. You might have noticed a pattern and also a trend, and we're going to use this pattern. You might have noticed that the probabilities are getting smaller as the number of people in the room increases, and if you think about it, that makes sense. Our goal is to come up with a neat way to compute the probabilities when there are k people in the room, and that's what we're going to do next. Suppose there are k people in the room, suppose there are k minus 1 people in the room with different birthdays. There are going to be 365 minus k minus 1 blue days and k minus 1 red days. Suppose another person enters the room, and let's call them person k. The probability that all of them have different birthdays, or the probability of AK, using the same principle that we used before, is the probability that k minus 1 people in the room, or the people who entered before, have different birthdays, and person k has a different birthday from everyone else who entered the room before, or the k minus 1 people. Now, if you remember, we also made an assumption about independence. We said people are born independently of each other. And we can use this fact to show that the two events here, this event and this event, are independent. Now, since they're independent, these become their own individual probabilities, which can be multiplied. And we can also rephrase this event, the probability where person k has a different birthday from k minus 1 people, as the event where person k was born on a blue day. Now, we can write this as probability of a k minus 1, which is the probability that k minus 1 people in the room have different birthdays, times the probability that person k was born on a blue day, which is 365 minus k minus 1 divided by 365. And we use this fact that there are 365 minus k minus 1 blue days. We now have a nice recursive formula for computing the probabilities for any k. Next, we use this formula to find the probability that 23 people in the room have different birthdays. This is the formula we had before from the last slide. We computed A3 some time ago, and we used the same approach to compute A4, and we use A4 to compute A5, and so on until A22. Now we know that the probability of 22 people being in the room and for all of them to have different birthdays is 0.525, which is a tad bit more than 0.5. And we're going to use this formula to compute the probability of 23 people in the room having different birthdays. And this, plugging it into this formula, we get 0.525 times 343 divided by 365, which is 0.493, which is strictly less than 0.5. The quantity we really care about is the complement of this event, and we're going to use the law of total probability to compute this as 1 minus this event, which is 0.507, which is strictly more than 0.5, thereby proving the birthday paradox. If you like this video, check out part 2 where I talk about a more general version of it. There's also part 3 where I talk about the applications of the birthday paradox in cryptography, also known as the birthday attack. I will be making more videos in future, so don't forget to hit subscribe. And if you have any questions or comments, I'll be really happy to answer them. I'd also like to hear from you about what videos I should make in future, so please let me know. And thank you for watching. La 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 la.